I'm Kris Kimel with Humanity in Deep Space, and welcome to another one of our webinar episodes, which we've been doing now for about a year. These webinars are an attempt to bring together a lot of really interesting ideas and concepts and people that explore how we as humans are going to survive and thrive in deep space. Going into deep space, leaving our planet is in fact a planetary issue and problem. And we're very proud of the fact that our webinars not only attract hundreds of people in attendance, but also generally people from 25 to 30 countries all over the world. And so we are in fact beginning to gather together and get the ideas and in participation of people from around this planet, which is very, very important.
Welcome to Humanity in Deep Space, Episode 6, The Mind in Deep Space. Hosted by Kris Kimel, and with our panel, Phil Kraemer, former chair of the psychology department at the University of Kentucky, Greg Schmidt, director of the Solar System Exploration Research Virtual Institute and co-founder of the NASA Ames Space Portal, Diane Snow, who holds a Ph.D. in neuroscience from Case Western Reserve University, and Alexandra M. Whitmire, deputy element scientist at the NASA Human Research Program.
I want to welcome you to our first webinar for 2022. As you know, we had a whole series last year. We kicked off the initiative project in 2019 with a live event, and then the pandemic hit, and we've had since transitioned to a series of webinars. I will let you know that we are looking at a possibility of another live event next year to bring people back together, which I think is an important part of all this conversation as well. But I want to welcome everybody. We have over 250, 60 people registered from 30 countries. So a lot of people from around the planet that are tuning in, and we really, really appreciate that. And that's one of the things we want to do is have a planetary conversation about all this. Before we start, I'd like to thank our sponsors that make all this possible. One, Kentucky Science Technology Corporation, National Stem Cell Foundation, the Solar System Exploration Virtual Institute at NASA, the Children's Center, Baird, Private Wealth Management, Space Tango, the START program, 22 Solutions, Higher Orbits, and the Media Collaboratory. I want to thank all of those who make not only this possible, but support our activity through the year. So today we've got, I think, a really interesting topic, that the whole issue of the mind in deep space. What we'll be really dealing with is the whole question or the issue of our bodies, our minds are obviously the result of over 3.5 billion years of evolution within the parameters of Earth, zero G and all the other things that involves. And of course, what we're about to do as we transition to deep space is really put our understanding and our resiliency of our mind and bodies to the test. Certainly we are already a spacefaring species. We've been in space since the 60s. Humans, we've had people on the moon. We've had people living and working in space for over a decade. And of course, the robots on Mars are really simply an extension of us as humans. And so we clearly are already a spacefaring civilization and species. And now as we make, as NASA and others are making major inroads now in attempts to go back to the moon, as well as onto Mars, along with a lot of private companies, we're probably closer now than we've ever been to having actually habitats on the moon of some sort, and then onto Mars. And that presents all sorts of really, really interesting, but very hard problems for us to deal with beyond just the technology issues and problems. So that's what we're going to be talking about today. We have a great panel lined up. I'm going to ask everybody to briefly introduce themselves. And let me start with Diane Snow.
Hi, I'm Diane Snow. I got my Ph.D. training at Case Western Reserve University and the University of Minnesota. Shout out to Jerry Silver and Paul Letourneau if you're listening. And went to the University of Kentucky for my assistant, associate, and full professor and endowed position with the brain and spinal cord injury group there. And got into administration a little bit, trying to help young people get their start in science as well, and did the undergraduate research director and also worked with the honors community a lot. I'm very recently retired and looking at the next chapter.
Yeah, and Diane also has done a lot of thinking and work in the area of looking at exomedicine, or the whole issue of looking at applications in zero G that might be for Earth. Done some work with Space Tango. So, Phil.
Good afternoon. I'm Phil Kraemer. I'm also from the University of Kentucky. I say from because I recently retired after over 30 years, despite my youthful appearance. That surprises you, I'm sure. I am a cognitive scientist. I like to think of myself as an evolutionary psychologist as well, which is a flavor of cognitive science. And I'm still trying to learn as much as I can about the human mind. My recent activities have to do primarily with creativity and curiosity, but I'm also becoming very deeply interested in the psychology of belief. But I look for any kind of topic that lets me kind of use my own creativity and learn as much as I can. And this is one of those topics.
Thanks, Phil. Greg Schmidt.
Thanks, Kris. My name is Greg Schmidt. I'm the director of NASA's Solar System Exploration Research Virtual Institute. We're one of the sponsors of this series of talks, and honored to be so. I've worked with Kris for quite a few years now, well over 20 years. We've started a lot of things together, including quite a story behind this, but including what was originally Kentucky Sat, the first state-run space program, if you will, which eventually became Space Tango, that is now actively working with our International Space Station. So very proud of my involvement in that. Before this current job, I was at NASA headquarters and worked on a variety of programs there, including a partnership with the National Cancer Institute for early detection of breast cancer, and employing some of our NASA technologies to look for early signs. Proud of that as well. And then before that, I was a manager of a number of payloads on the space shuttle, and also helped start astrobiology. And if we have time later, I'll share a very relevant conversation I had with Dr. Mae Jemison once before her mission. She was the first African-American woman in space, and has been a dear friend ever since.
Thanks, Greg. So to kick it off, I'm going to ask, Sandra who's, if you've had a chance to go to her site, has done extensive work in this with NASA, and just to kind of briefly kind of summarize, I know it's hard to do in a brief amount of time, kind of what we currently understand, what we think we understand and know about the kind of neurobiology, neuropsychology of humans in space.
Yeah, thank you very much, Kris, for the introduction and the opportunity to meet with you all today. I'm Sandra Whitmire. I'm part of the NASA Human Research Program at Johnson Space Center. And where I sit is within the part of HRP, the Human Research Program, that oversees research related to psychology and human factors. And there's other groups in HRP that also look more on the physiology side. We have another group that's also focused on radiation, and then another one focused on medical care for future missions. So within HRP, our focus has been, really trying to understand what are the gaps in knowledge that we have and the gaps in mitigations when we think about where we are now relative to spaceflight, relative to missions in low Earth orbit, and where we want to go with a Mars mission, a long duration Mars mission. And even now we're talking more and more with lunar missions as we think about getting that presence on the moon that Kris spoke about. Are we ready to do that? Do we have the type of ground support that we need? Do we know what type of crew we need to select and how to support them through these missions? And so in order to understand, and from where I am with in the Human Research Program, in human factors and behavioral performance is what our group is called. We focus on trying to understand and mitigate adverse behavioral outcomes that could emerge from an extended long duration to Mars. We also look at sleep, circadian and fatigue and workload in these types of missions that could emerge. We think about and do work relative to supporting teams. So when we think about individual performance and individual crew health, we know that this crew that's going on these missions are going to be functioning as a team. And so we think about team level outcomes and ways to support the team as a whole. And then from the human factors component, we look at how to design the vehicle in a way to really support the crew under these unique circumstances, or design the interfaces, or think about the layout of the vehicle and so forth. So the human factors component kind of being that partnership on the psychology side. And so to your question, Kris, sorry, because I've rambled on a while as it is.
No, that's great.
But relative to what we know in these areas, we have research underway to really help us understand as much as we can, without simulating a 3-year mission to Mars. We try to leverage research and conduct research that's done on the space station with crew members that are up on orbit from about 4 to 6 months. We've had a couple of extended 1-year missions. Mark Vandehei, who just returned, coming back with another 1-year mission. And so we collect data there. But, ISS, it's a great analog for us. But when we think about Mars, there's some key differences that we have to consider. So one key difference between ISS and crew on a mission to Mars, well, there's the duration there, with Mars being closer to 2.5 to 3 years. Mars will also introduce unique stressors such as the galactic cosmic radiation. So we're really trying to understand the effects of GCR on the central nervous system, and also things like communication delays. So it will be at least about 19 minutes to get communication one way, 19 minutes back. And so how will that affect how the crew functions as a team? Right now, ISS is really developed to have that close tie with mission control, and that they work. It's a true partnership and facilitated largely by the real-time communication. So just that psychological aspect of being now socially isolated in addition to being physically isolated in these future missions. So ISS presents a wonderful platform for us to conduct research, especially when we're talking about the physiological ramifications of a Mars mission, because we have altered gravity there. They're in weightlessness, and there's really no other way to understand physiology and biological changes in that type of an environment. Can't really simulate that on Earth for extended durations. But to get at sort of more that extended isolation, we also conduct research in what we call isolation analogs. So we have analogs or platforms where we can collect data, and we're simulating that level of isolation that we anticipate on a Mars mission here on Earth. So we have research at Antarctic stations that last, around a year, and you have a small team there that's isolated for a long period of time. We also have kind of isolation chambers where a crew of 4 to 6 individuals will hunker down, simulate like they're on a planetary mission. But that gives us a chance to understand some of the ups and downs, and even in high-performing individuals, what are things that when we can simulate the calm delay and that physical and social isolation, what are the risks that we can see and kind of get ready for? And then lastly, on the radiation side, it's a very difficult one for us to tackle, as you can imagine. But there are a series of investigations that we do with rodent studies, and we try to understand as much as we can also from radiation exposure here on Earth, although our cohorts are very different when we think about astronauts that are very healthy versus cancer patients. So we have to be careful how we make inferences. But we try to do as much as we can to learn from these environments, and then hopefully collectively we'll gather the knowledge that we need to really support our crews in the future on these unprecedented journeys.
Thank you. Also, for those tuning in, feel free you can ask questions, go online and ask questions through the chat application, and we'll try to get to as many of those as we can. Thank you, Sandra. Let me following up on that, let me ask everybody else, we talk a lot about isolation, but also I'm interested. In fact, I think I saw an article recently where Sandra was quoted saying there are different types of isolation, obviously, and what we're going to be experiencing in space is quite unique. But also talking about the mind-body interface and the whole kind of neurobiological aspect of this, particularly this unprecedented issue of spending, 3+ years in a zero-G environment.
Kris, I could take an initial
Sure.
stab if you'd like. Yeah. Well, one thing that I would like to share is a perspective on what this journey is going to be like. And I don't have the expertise of Phil and Diane, but I'm a longtime NASA person, thought about this a lot. And so when you think about it, going to Mars, it's many months. It's a journey that takes approaching a year. And then you stay on Mars for a while, and then you return with another journey that takes about a year. So you launch from Earth. At first you see this wonderful globe that we're all so familiar with from the Apollo shots. But as you leave the Earth vicinity, that globe shrinks and shrinks until the point where it's just basically a bright blue point of light. Most of your journey to Mars is going to be like that, where you're not even able to see a disk at all. You're seeing a point of blue light. And then on the other end, you're seeing a point of red light that's getting brighter and brighter and brighter and eventually turns into a disk. And so what I want the audience to think about is what I think is a really important perspective on isolation. And that's that for most of the journey, you're not going to be accelerating. So you're going to be in microgravity, what most people think of as zero gravity. And you're not going to have any sense of at all that you're even moving. You're going to be suspended in deep space with as I mentioned, gradually dimming bright blue point of light and gradually brightening red point of light. And so I think that the work that Sandra and her team do at Johnson Space Center is absolutely key, because this is going to have enormous effects on us as people. So I'll stop there because I know other panelists have comments.
Sure.
That's fascinating. And something I just learned from a friend of mine who came back from the station last fall is kind of counter to what we might think. First of all, astronauts tend to be what we call type A personalities, right? So they're busy and thinking all the time. And you would think that astronauts have so much work all the time that they're overworked continuously. But when I was talking about what kinds of stressors you had on the station, this person told me the worst stress that we had this last time was that there wasn't enough work, and that they would spend some time watching Netflix movies or reading or whatever. And they're thinking, I came all this way and did all this career to make a difference, and here I sit doing nothing. They want to be busy. But when we're looking at a trip to Mars, just like the perspective that you just presented, Greg, what it's going to look like at the human level, that's a lot of downtime. And there's only so much to be done. As humans, we have a small space there and not much to do. That's going to be very impactful.
Yeah. Phil, I know you want to say something.
Yeah, it's fascinating to hear this conversation, and I'm very interested to know that Sandra and her team are really trying to explore this. It's a tough one to explore, though, because the ultimate kind of consideration is something that's very hard or impossible to simulate, and that is, what if you are out there for 6 months? And you can't really do that in a simulator on Earth, because you can always tell yourself, I can open the hatch and escape these mad scientists. And you really can't do it on a space station, because there is that big, beautiful orb that Greg talked about, and you feel that connection. So we're really having to speculate about something for which we don't really have any empirical evidence or experience with. And that's what makes this kind of fascinating. There's a part of me that wants to trust our creativity and our curiosity. Yeah, the fact that we do a lot of things that weren't designed to do by nature. But it's also the case that we are of Earth by Earth. And a lot of the attributes that we have in terms of our behavior are entrained to being on Earth. So our biological rhythms, for example, we have diurnal rhythms, we have monthly rhythms, we have seasonal variations, and we react to that in a way that the body and mind are both sort of affected by that. And it's very hard or impossible to stimulate that kind of thing. So it's encouraging to know that we're trying to spend as much time and energy thinking about what it's going to be like. But it's interesting that it's really like nothing. And that's going to make it hard.
Let me follow up with Sandra, and others can comment too. Sandra, since, as you mentioned, since there's really no way to simulate the actual mission, early mission to Mars, and I think that's what we're talking about, is really the first 50 years or so, not 500 years from now when we've kind of figured it all out. But since we really can't simulate that to any degree, really, I mean, the longest anybody's been in space and with orbit is simply a year. And I know there's no answer to this, but I'm going to throw it out. So how do we prepare for all, many of the eventualities that are going to potentially face us in a 3+ year early mission? And what, how do we even do that? How does NASA thinking about that?
Yeah, it's a great question. And it's part of really, it's HRP's sort of focus is how are we going to do this, right? So acknowledging, and I completely agree with Phil, there's no perfect platform. There's no way that we can really simulate this full mission and do it enough, let alone do it enough times where you have confidence in your data, right? So the best that we can do, we're really trying to do the studies that need, the changes that we see, the physiological changes that we see on orbit. Studies where we need to understand the aspect of weightlessness. We sponsor research looking at those types of outcomes. And we've actually have had some recent publications come out through NASA HRP and also through our international partners trying to understand neurostructural changes that result from space flight that we associated with space flight. And so there's a series of studies that are showing us that there do appear to be, I can never say this word, but anatomical changes, my apologies, that occur in the brain. We see gray matter volume changes, we see expansion of certain ventricles, we see an upward shift of the brain in the skull, redistribution of the cerebral spinal fluid in different aspects of the brain. Some of these changes seem to persist post-flight, but what we haven't seen yet are really those functional outcomes that are tied to those changes, right? So we've observed these through measures such as pre and post mission MRI, but we don't see them really as a precursor yet to functional changes. It could be a measurement issue. It could be that so we do have plans to study individuals pre and post flight more thoroughly to understand, as we see these changes in the brain, are they clinically significant changes, or is it just a matter of the body adapting and then the body adapting back and we can compensate? So that's sort of a remaining, a question for us as we further our research. And that type of question is really where we want to focus a precious resource like the ISS, and we want to ask that type of a question. When we start thinking about issues related to communication delay and how we're going to deal with a medical emergency under conditions of communication delay, we could implement a study like that on ISS, but really the ISS was developed to be, again, dependent, working hand in hand with mission control. They have real-time communication. That is a structure that's really intended for the current type of operational paradigm that it's in right now. But we do have research in isolation analogs where we can include that communication delay protocol and work in these types of medical scenarios to help us understand what are the risk factors associated with that, with the communication delay. How do we need to better equip the crew going forward as they have to handle these types of emergencies on their own? So we really do try to take into account the uniqueness of the analog, or I guess the requirements of the question, the research question, and what is the best fit platform for us to understand. But unfortunately, we just don't have the opportunity to study it all comprehensively in one place in that same paradigm that we would see a Mars mission. So it's that vast portfolio and trying to do the best that we can, trying to really do due diligence with the resources that we have to target our questions and our forward work.
Sandra, I was reading your papers that are tremendously interesting and wondering from a neuroanatomical perspective, some structures that are really vulnerable with those fluid dynamics and the shifts that happen in the ventricles are like the hypothalamus or pituitary. And those regulate so many of our functions, especially a major one being stress, the cortisol response. And all these astronauts that speak about their experiences there say stress is a really high component for their experience. So do you have any, from your research, are there any things that show that those are particularly vulnerable in this particular scenario?
Yeah, it's a great question. And we have get to work with a wonderful team and people who are have more expertise in this area than I do in brain function. But we've identified kind of similarly that on Earth, where we see some of these types of changes, it could be concerning. And so while we have studies completed on ISS, there's a recent study that I think a publication just came out earlier this year from Chris Jones. It's from David Dinges and Matthias Basner and team. And one of the measures they included, it was a fatigue study looking at psychomotor vigilance testing primarily, but they also included some subjective measures over the duration of a 6-month mission, and found that about half the crew members reported just steady increase in subjective stress. And so not all of them did. Some had a decline, some were more even keel, but about half of them, you could see the steady tick up on that self-reported stress like you're talking about. But that's one cohort of data that we have that unfortunately is a different cohort than where researchers were able to come in and do these pre-post assessments. So to your point, we really recognize that's very important. And so our forward work and studies that we have currently underway, we actually have a complement of studies that's supposed to begin very soon that's looking at multiple body systems, subjective and objective data, and trying to thread these pieces together. So, and that does include a pre and post neuroimaging, and as well as a deeper dive into the cognitive changes in flight and spatial cognition changes as well, along with some of these subjective reports. And in conjunction with that, we're also looking at immune changes and other physiological changes to kind of get, hopefully, a better picture. Because as you note, really importantly, that we recognize that there are potential operational meaningful outcomes that are associated with these changes. We just haven't studied it comprehensively enough yet. So hopefully this assessment will help us understand it more fully.
Let me ask a question. It was during our during the Apollo days, we kind of eased into this with Mercury and then Gemini and Apollo, and we went around the moon and back. Has there ever been, and maybe this isn't practical, I'm asking this without knowing any of the technology challenges, but has there been any thought to, instead of sending, the first trip is to Mars, to sending people out into deep space for, 2 to 3 months and then have them return and kind of try to get a handle on some of these things before we embark on a three-year mission? Greg, is that something that's been discussed within NASA or by any of the private companies?
Yeah, I can't speak to the private companies, although Elon Musk has made his intentions fairly clear in terms of Mars. I can, though, speak to our gateway, which is going to be in a rectilinear halo orbit around the moon. It's a very unique kind of orbit that places it in deep space. Now, this is not the kind of deep space perhaps that you're referring to where we're, where we can only see points of light. We'll still be able to see the Earth's disk and the lunar disk, but we'll be well beyond the protective field of the Van Allen belts. We'll be subject to the full onslaught of solar radiation and the dangers of that. And so yes, this is part of our NASA architecture in terms of how we're going to be dealing with that, and that'll have its own unique challenges. And I wanted to also, while I have the mic, address your other question with another perspective as well. And you and Sandra both correctly mentioned about the complexity of missions and the need for flexibility. When I reflect back on the mission that Mae Jemison, who I mentioned, flew on, that was an 8-day mission, and we had everything planned, almost to the minute, where the astronauts were kind of complaining about not having enough free time. Things, as we're talking about, as Diane mentioned, are changing in terms of free time. But there's another factor as well, and that's that as we go further and further from the Earth, the round trip light travel time is going to get to a point where Earth cannot respond to emergencies. There's the whole situation, looking back to Apollo 13, Houston, we have a problem. Well, we're going to have to deal with that problem ourselves. And I'll mention something that is not oftentimes discussed, but I think is going to be a huge factor in this. I was on a science organizing committee for a workshop on the next 50 years of planetary exploration. And I suppose it's the fact that I live in Silicon Valley, that helps with this perspective. But I think that artificial intelligence is going to be a really enormous factor in all of this. And I like to think of this as us bringing on a different class of astronaut with us that's going to be increasingly capable, increasingly intelligent, able to have conversations with us, that could address some of the psychological issues, and certainly able to help us solve some of the problems that we're going to be getting into. So now I can't speak as Diane and Sandra certainly can to the physiological changes, but this could definitely be an assistant to us, and this will very much be happening in future missions. Every mission beyond perhaps 10 years from now will be carrying astronauts, if I can call them that, of this sort.
Yes, I'm going to ask one quick question, and then I'm going to get on to some of we've got actually a lot of questions that have come in, and some of them are pretty interesting. We talk a lot about this body, mind-body interface, which I think is so important, and I think is one of the really hard problems that challenges us in our future exploration efforts. We talked about, brain circuitry, what happens to the microbiome in deep space and the relationship to the brain. But one of the other issues, I think, which is oftentimes not talked about very much, it's not that it's not addressed, it's not that people don't think about it. Again, this whole mind-body thing in deep space is that, I've had some conversations, for example, with Robert Thomas, who's a former admiral and Navy attack sub commander. And we talked a lot about a lot of things, some of the analog issues that might arise in these subs, which go underwater for 3 months. And one of the things I asked him was, what's the most important thing once you've done the crew selection and training and all the other things that we think about? What's the most important thing in keeping everything on an kind of an equilibrium on these subs? And he said the answer is food. And of course, food on subs is a little bit different. They have freezers. They can hold a certain amount of food. Oftentimes, I think NASA has actually sent chefs or the Navy to train with 5-star chefs. But food is going to be a real problem in deep space because you can't take a lot of stuff with you. preparing food for astronauts on ISS is is much less difficult than thinking about that. I just want to just throw that out. That's just one example of something that's going to be something that is so essential in our lives as humans since the beginning of time, and we really don't know, I think, how we're going to deal with that. Phil, do you have a thought? I know you and I've talked about this.
I have no thoughts that are worth expressing on that. I think and that's what I find so interesting about this whole topic, is that it really involves a chance for us to be creative and to speculate out there. But I think the more time we spend trying to anticipate some of these problems, and I'm very encouraged to hear what Sandra has to say and Greg. It seems like there are people working on this one. Because I even, question myself, how do you select the crew? Is it going to be just one gender? Is it going to be mixed? Is it how many? What kind of psychological attributes do you look for? And I think that the challenge is that it's unlike other kinds of space missions. This is not the same as going to the moon. You need to have people who are able to sort of manage a very abnormal environment where all of the props of Earth are gone. And I don't know how we kind of select for that, but I'd be interested if Sandra or Greg have any thoughts on how you go about selecting who goes up.
We'll get back to that question. I want to get to some of the questions that have come in, if you don't mind, because there's something. One of the questions that came in is just, I think we can answer these hopefully fairly quickly. So what's the difference between is radiation exposure more problematic on Mars than it is on the International Space Station or on the moon?
Yes, and I'm not smart enough to give you the specifics of how, and maybe Greg can help fill in, but when you start getting past our atmosphere and where ISS is part of, you get into closer to the Van Allen belts, and now the crew is exposed to heavy ions and a level of radiation that we do not experience here on Earth. And so there is a laboratory where we can simulate that level of radiation, but not on humans, obviously, and it's used with small rodents but it is a different type of radiation than what the crew experience on ISS, and the doses, the amount is different as well. The exposure is much heavier en route to Mars. So that's one of our biggest hazards and concerns for these future missions.
Yeah, and just to add, absolutely agree with Sandra. We're protected in low Earth orbit by the Van Allen belts. These were discovered by James Van Allen, a professor at Iowa many years ago, and this is due to the Earth's magnetic field and trapping energetic solar particles. My institute actually does research on this and takes a look at, amongst other things, solar bursts, high energy bursts from the sun, and in answer to the person who raised the question, the moon is going to be a really tough place in which to deal with such things, and we're having to pay attention about things like the solar cycle. The sun is on a 26-year cycle, and we're now on the upswing in terms of the energy of the solar emissions, and that has potential ramifications in terms of these high energy solar bursts, which would be very devastating to astronauts. And so we're having to think about how do we protect these astronauts from these high energy things. Can we use the lunar regolith, for instance, which is the soil, if you will, that is ubiquitous on the moon? Can we do 3D printed structures with this regolith, which is something that my institute has also taken a look at. So yes, the radiation is a huge problem. It's something that we have to deal with, and And it's even tougher when you're in transit between Earth and Mars, because you have a fairly thin-skinned spacecraft that is not going to be able to entirely protect you. So it's a difficult one that we have a lot of work to do still.
Getting back to something Phil said earlier, and Diane alluded to, AI and some of those issues. One of the questions was, how much do we think that virtual reality might play in these long missions in helping people cope with some of these issues of isolation and other kinds of things?
Kris, just before you move on to that, related to this last topic, it brings up two shortcomings, I think, in the research that we have to date. And that is a lot of the GCR, galactic cosmic radiation studies that have been on rodents. So we can only translate so far from the animal research that's been done. And they've looked mainly at males. And the work that has come out comparing males and females show differences. And I wonder a lot about what the differences will be on male and female bodies in this new environment, and especially related to cosmic radiation. And there's been some suggestion when people like us are just sitting around pontificating that we may be able to select humans who have a genetic composition that make them less susceptible to the effects of radiation than others. And that's mind-blowing, I think.
Yeah.
But the male-female difference is one that's on my mind a lot, about how much we can learn before we put people in harm's way.
Phil, do you want to say something about the virtual reality / AI kind of
Well,
question?
I think that's a very useful creative tool, but all of these tools only go so far. I mean, virtual reality, as we have learned by being locked down in higher education and having to teach in virtual classrooms, virtual reality lacks something that normal reality has. And I think how we design these virtual reality experiences is going to grow the more we spend time doing virtual reality. But I think there's always going to be a limit to how far that is going to take us. And I think it's also potentially easy to make some mistakes along the way, that we design systems that in the long term can produce some harmful after effects. So, again, I don't want to be this curmudgeon that's downplaying all of this, but I guess I'm more, I'm not going to be on that space capsule this time. I can't imagine my own personality being 6 months away from
There's
Earth.
no way they would select you, Phil.
I hope not.
You'd get screened out in the first 5 minutes.
But again, I come back to that question. How do we select the best sort of crew for this kind of thing? And I don't know that we have all the tools. Really.
One of the things that somebody asked, and I've heard it discussed before, and I'm going to paraphrase. They said, well, the question was, given all of this, why do we need people? Can't we develop robotic technologies and things like that? And I've always felt personally that ultimately humans will be there. I mean, that's just in our spirit, in our DNA. But on the other hand, I think there's maybe a middle ground. And the question is, which I've heard other people say, should we not send humans until we've absolutely completely exhausted the cutting edge of technology with robots? Thoughts on any of that?
I'll take a first crack, and I would say definitely not. We're never going to solve all those problems, right? I mean, we're always going to have problems, and I think that we have to come to a point where we have an acceptable level of risk. Now. However, I want to underscore the importance of the human research program that Sandra is one of the leaders of. It's critical that they have done a remarkable job at organizing and categorizing all of the risks, and then focusing on the key ones. And I've been following them for decades now, and it's truly amazing what they've been able to to address. I wanted to also give my perspective anyway on a couple of other questions. The VR, for instance, my institute is also doing research on this. And one of the things in particular that this is useful for, and I'll go more towards the AR end of the spectrum for this, is live control of things on planetary surfaces. And so, for instance, I mentioned the gateway a little bit earlier. That's going to be in this orbit around the moon, and it's going to be at a sufficiently close point such that via AR technology, astronauts will be able, on the gateway, will be able to control robots on the lunar surface, doing things like laying out low frequency antennas for looking at the early universe. So I think that this is, in certain key cases, this is going to be a really important set of technologies. And I also wanted to address Phil's point about how you select crew, and introduce one factor that a lot of people don't speak of, and that's resources. We are humans. We take, we have an environmental support system on every spacecraft that we bring up, and including spacesuits, which are their own spacecraft. And so minimization of resources is really key. And one of the things that I say often is, quite frankly, an optimal crew from that standpoint would be all female. And would be simply because men are larger and men take more resources, be it oxygen, food, water, whatever. And so I just wanted to put that out there as well.
Another person asked a question about any thought. I mean, we've seen this in all the science fiction movies on these trips to Mars. The whole issue of being able to execute artificial gravity on the vehicles.
You're asking, are we able to do that?
Well, yeah. Well, are we really able to do that? And what about that? Because we do see that in almost all of the sci-fi movies that come out. There's always usually some kind of artificial gravity going on, and we don't hear a lot about that right now, at least.
I was listening to an interview between astronaut Victor Glover, and Tom Cruise. It was just interesting to hear all his perspective. And he was talking about that and saying that was completely unrealistic just for the physics and dynamics of the spacecraft, that you couldn't have some part of it rotating like that. Is that true, Greg?
It's expensive is the issue. I mean, NASA's done sponsored various studies on it. It can be done. But there are risks, like I think you're mentioning, Diane, and there are, and it's just bottom line, really expensive. There's a lot of structural considerations. For instance, if you're spinning something, what that means is the outer areas where humans would live are going to be under a lot of stress, simply because of their spinning and their effective weight, and so that creates stresses that wouldn't be there in microgravity. So the question kind of goes to something perhaps for Sandra, and that's, how important is it? Number one, and at what level? At what? And so for instance, is the 1/6 G that we experience on the moon, or perhaps the 1/3 G roughly that we experience on Mars, is that enough for human physiology? I don't know the answer to that. Sandra, you might. I don't know.
Yeah, no, it's a great question, and I concur with your assessment, Greg, as far as the expense of it. We've done just very little research. There's a recent study that was done with a spinning centrifuge with people kind of in bed for 60 days. And so we're just starting to see results from that. I can tell you from a psychological perspective, it was a little bit more limiting. It's just inherently isolating in itself, just the logistics of the study of the participant having to lay down. We didn't see any, cognitive changes or anything that occurred in the continuous condition, and even they had a condition that was intermittent spinning. But as far as implementing artificial gravity, it's true that you would maybe mitigate some of the bone loss that's seen and some of these other changes that we're concerned about, but it does bring into question other risks in addition to the expense. When we think about partial gravity, I think we're starting to understand that, but it's one of those things we go back and look at research from the Apollo days and try to understand, what do we need to do to help facilitate their sleep? On ISS, in weightlessness, they can kind of just get in their bags, and some of them report sleeping really well. For others, it's a bit tougher, although it's probably a workload related issue a lot of times. But in that partial gravity, how can we make sure that we're providing the right support, the ability for them to lay down flat and live and sleep in that environment? So the partial gravity question is a really good one, and I think one that we're need to understand more. But I agree. In HRP, we sit more on the side of that artificial gravity is probably not something that we will see come to fruition. So our assumption is that the crew will be sort of in weightlessness en route to Mars, and then in that partial gravity environment while on the Mars surface. And then weightlessness.
The question
back.
is the technology, just a quick, is at least according to the laws of physics and technology, is it, theoretically, is it possible? It's just a cost, or is it something that people don't think actually is actually able to happen, period?
That I don't know, Craig. Oh, go ahead.
Oh, no, go ahead, Sandra.
I was going to defer to you because I know that the concept of understanding human physiology under a centrifuge is different than an actual spaceship. So I was going to defer to you for your response on that.
Sure. And so, Kris, there's nothing in the laws of physics that would prohibit this. It's truly a matter of cost. And so for all of us who love 2001: A Space Odyssey and think of the giant centrifuge, absolutely. Now, that could be done. How many trillions of dollars it would cost to do that? That's another question. It's tremendously expensive. You would have to have better propulsion systems. You would have to have stronger support systems, and the question then becomes, is it worth it? And I would side with Sandra that it probably isn't, but we might not have the final answers yet.
I want to circle back just for a second on something I mentioned, and there wasn't a whole lot of conversation about it because I happen to think it's really one of the real. And I get back to this issue of food, just because it's so central to the history and the psychology, sociology, and biology of humans back to the beginning of time, and the fact that it's unrealistic to think that people are going to eat sunflower seeds for 3 years or whatever it is. And I know NASA has food lab, and again, Diane and I have talked about this just brainstorming. But how are we? Seriously, how are we going to try to meet this challenge as opposed to, even if you assume, the first thing you can do is do the math, assuming that an early crew is, we'll say it's, 8 people, whatever number you pick, everybody decides it's good for 8 people. First thing you got to figure out is how much food, nutrition, all the other things are 8 people going to need for 3+ years. And it's going beyond nutrition because, as Sandra talked about earlier, in terms of astronauts working, they've got to be able to thrive on these. They've got to work on these trips. So it's not as if it's just like, oh, we just need to keep them alive.
Kris, something to think about from a neurophysiological perspective is the sense of smell. Mm-hmm. And smell is so
really good.
Linked to food and our drive to eat. And it's also very vulnerable to insult under these conditions, fluid dynamics changing rapidly and various effects on structures of the brain that are involved with that. In fact, our olfactory system is one that can regenerate, unlike most of the rest of the brain, because it has constant insult. And Mother Nature has provided a way for it to continue to grow new cells for that reason. But they're linked tremendously along with memory and cognitive function as well. But if we don't have a drive to eat, that might even be another component. There's so many levels related to food, of course, but that's just one of them. What if we see that kind of result?
Yeah, Diane, that's an excellent point. And but it's my understanding that just generally speaking, crew tend to eat less on orbit, come back with some weight loss. So we think that there is something potentially happening there with that fluid shift, potentially changing their olfactory system and losing that appeal for food. It could be just as they tend to be busy. I know you mentioned your example of a crew member who reported not being busy, but typically it's very busy. And so when we get busy, that's maybe a factor that goes into losing that interest in food. But it's a great question. And, we're really trying to understand, there's very smart people at JSC across NASA trying to figure out that mix of the right nutritional composition that the crew is going to need for the survival piece, but really the appeal of the food, making sure it's palatable, making sure that they're going to eat it a month, 6 months from now, even though it's part of a limited menu. And it is a struggle just because of those volume constraints, and I don't know logistically if there will be opportunities for maybe cargo supplies to sort of help replenish the food so that there is a bit of a boost there, some more options, because that is a limiting factor, but there's some wonderful scientists that are really trying to figure that out and really advocating for the crews in these future missions to have that right supply, because there's a general acknowledgement, as you mentioned, about how important it is.
Yeah. Somebody just made a comment. I believe I know this person from NASA, but I won't mention the name, but said Greg addressed the above question a bit but it said the Chinese lunar palace, I guess, had 2 female crew members and 1 male. And this comment says, according to the director and the research, the 1 crew member ate as much food as 2 female crew. So if that is in fact accurate, which I assume it is, that's pretty interesting given what you just said, Greg.
Yeah. I mean, this is, I'm very serious in making this suggestion. I mean, this could make a very big difference in the cost of the mission and the size of the spacecraft and whatnot. I mean, this is a consideration, for instance, in how much material we're going to be able to bring back from the moon, how many samples and everything. And so if we on the one hand have say a couple of women that are perhaps 110 pounds each versus a couple of men that are 180 pounds each, that's a really significant difference, in the amount of environmental support that each of them needs, but then in the amount of things that we can bring back. I want to comment on something else as well that I think is relevant, and that's that we will undoubtedly have to grow our own, in terms of food. A dear friend of mine, now retired from NASA Ames, Mark Kliss, was the inventor of something called the salad machine, and it was a device designed for shuttle and then space station use that would be able to grow plants, and particularly things that one would be able to eat as fresh ingredients. And so I think that's important, but it's important for another reason as well. And I've heard this both anecdotally as well as talking with astronauts, and the other panelists might have comments on this. And that's that seeing life that's growing, in other words, things that are other than humans, is really important. And so when our astronauts were on board the shuttle Mir program, the Mir space station of the Soviet Union, they spent a lot of time tending to the growth of the plants and the various other animal experiments that were going on. And I think that this appears to be a big psychological benefit. I'd be interested in what the other panelists have to say about that.
Yeah, I think that's interesting. Go ahead. I'm sorry, Dan. Go ahead.
My friend who came back from the station was saying how incredibly valuable fresh food is, and we've all touched on that one way or another. Phil talking about your link to nature and your comments about fresh food, Sandra. and said that morale was really high when the first shipments came of fresh food. But as that dwindled, it was palpable how the change in morale that took place among people knowing that they were going back to non-fresh food. So we've got to come up with some way to be able to provide that
Right.
long term.
Two things I want to go back to. One is I think it harkens back to something Sandra said earlier in kind of a passing comment about spacecraft design. We talk about, we think and we talk about growing, which is great, but there's a infrastructure and capacity issue here of, growing food for 6, 8, 10 people over 3 to 4 years, both in terms of volume. And again, I think that could be an interesting webinar in and of itself. And someone else raised it. We don't have time to get it. We just have a few minutes left. I'm going to ask anybody for a final comment. Also, one person based on this conversation asked, well, how will we keep, other than work, what will astronauts be doing going and coming from Mars and being occupied? And I also think that's actually a pretty interesting topic for another webinar. And that is, they'll be busy doing things, but on the other hand, what are they, how are they going to be occupying their time? Is there a role for, recreation, entertainment, arts and humanities, those kinds of things that might play a role in helping everybody stay, stay on an equilibrium and sane and occupied during that time. We're just about out of time, so I'm going to ask everybody if you have anybody just have a closing thought here. Diane?
Yeah, we tend to think a lot from a neuroscience standpoint of the effect on neurons, but there are 86 billion neurons in the nervous system, but there are 10 times as many non-neuronal cells in the nervous system. And all of them have very specific functions like maintaining synapses and neurotransmitter regulation and microenvironment and cleaning up debris and all kinds of things that are really important to normal human function. So I think we have to do a lot more study looking at what the effects are on those like microglia and astrocytes and Schwann cells and so forth.
Okay. Phil?
I would just mention what I think you hit on, Kris. There's an important dimension for the role of folly, and we have to sort of factor that in. I can't envision that the crews would be just working all the time. And it's very important to human beings to have this opportunity for play and recreation.
Sandra?
Yeah, no, I appreciate hearing everyone's thoughts. It's very helpful, and appreciate just a larger community mulling these things with us, and it's going to take a lot of hands on deck to really support our future crews, and to completely agree with the comments and conversation. I think Phil's question about selection, it's a good one, and it's something NASA's done really well. Our crew members really have just done an amazing job on ISS, but we see that shift to the different kind of individual, the different requirements towards a Mars mission. And so appreciate you bringing that up, and think that this is great food for thought for all of us as we go forward. Thanks,
Sandra. Greg, final thought.
I think that we're just coming out of this very long pandemic, and I think that one of the things that all of us have experienced is isolation, and it really brings to focus the importance of human connection. And I think that's one of the most important things to think about in terms of our future in space. Astronauts being able to connect with their families, their friends, and their communities, and with each other. And so I am very thankful, to my amazingly talented co-panelists here to have been privileged to be a part of this, and what a journey we have ahead of us.
Thank you, everybody. I appreciate everybody's time. I want to again thank our sponsors. You can also visit our website at humanityanddeepspace.com, make any comments, sign up to get our regular emails. And if you have any, a short article you'd like to write, submit, we put those on there as well. So again, for our panelists, for our sponsors, for Humanity and Deep Space, this has really been really, really interesting. Unfortunately, there's a lot of questions we weren't able to answer, but we'll try to get to those at some point. And on behalf of Humanity and Deep Space, I'm Kris Kimel, and thank you very much. I hope you enjoyed this latest episode of the Humanity in Deep Space webinar series. We'd love to hear from you. You can always check out humanityindeepspace.com, which is our website. It's also an opportunity there for you to leave comments and your ideas. And we very much want you and welcome you to let us know what you thought of it and any ideas you might have for content for the future. Thank you.